be here again. I talked at the very first TAMEST meeting on a very similar topic. So what I'm going to talk about today, what the innovation we're interested in, and it's a very difficult one, is solar fuels. Can one take sunlight and directly drive a system which will take in water, or more desirably in later time, CO2, and produce fuels? And so this has been a long-standing problem of interest in science. In fact, I was very interested in hearing Rich Templeton's talk at lunch, and he mentioned Jack Kilby. And Kilby, of course, is best known for the integrated circuit and the calculator. But in fact, Kilby, in the early 70s, came up with a solar energy system that was probably, and Texas Instruments developed it with DOE, that was probably the best still solar energy system that stored fuel in a practical and large-scale way. And so there was a lot of interest in this back even in the 70s in this kind of a field. So what do we propose? We propose a box. Just imagine a box. Into this box is coming water. Into this box is coming sunlight. And out of this box is coming hydrogen. That's the first one. The next level of that is, here's the box. Into this box is coming water and CO2 and sunlight. And out of it is coming a fuel, methanol, another fuel. Now, as soon as one gives you a scheme like that, you have to ask, well, first of all, is it against any laws of chemistry or physics? And the answer is no. And of course, we depend on photosynthesis. We've had examples of this over a very long period of time that do exactly that they take sunlight and water and carbon dioxide and can process it. So there's nothing that prevents you from doing this. Then what you ask is, how efficient can it be? What is the maximum efficiency? How much of the sunlight can I capture? And the answer here is useful amounts. There's already shown that you can get to things for hydrogen, 12, 13%. The maximum efficiency, depending how you do it, with 1 or 2 collectors and so on, could be as much as 30 or 40%. And so the theoretical maximum efficiency is okay. Then you ask, how about stability? I mean, biological photosynthesis has the advantage of growing anew every year. A system we build has to last for 20 years. That's still a problem. One has systems that work. If we have time, I can show you some. But the stability has not been demonstrated over that very long period of time. And the third issue is cost. And that's the biggest issue. Sunlight, there's plenty of sunlight to do everything we wanted. We can take a very small corner of West Texas and generate all the electricity and all the fuels we need. The problem is, how much is it going to cost me to cover that area to bring in the sunlight and to utilize the sunlight? And so that's the big problem. So within the context of what I was told to oh, I got to back up one now. Is this back up? So the example there is biological photosynthesis. We know biological photosynthesis can do this. Takes CO2 to sugar to lipids, takes water to oxygen. The problem with biological photosynthesis, as beautiful it is and as wonderful a system is it's not very efficient. Plants grow, but they don't grow fast enough to utilize the sunlight with anything like much more than 1% efficiency. And if you want to cover a huge area and make a lot of fuel, we've got to go up by an order of magnitude, probably 20, 30%. So the proposal is the right-hand side, then build a system, I won't go into the details of the system, where the water comes in and you convert the sunlight into an electron and hole, which is what sunlight does, and then you utilize those before they recombine. and do it at a fairly efficient rate. What would the impact be? Well, if there was a successful solar fuels industry, and I'm proposing that we try to build a solar fuels industry, it would transform society. We would have fuels available. They'll never run out. And it would have big impacts on energy security, on climate change, because we could get rid of the CO2 problem. It's going to take breakthroughs and rapid transformations, and it's not clear that we can really do it. The opportunities in the near term: hydrogen for fuel refining. Immense amounts of hydrogen are now used every day, billions of cubic feet, simply to refine petroleum. Immense amounts of hydrogen are used to make fertilizer, which is very important for agriculture. Ultimately, hydrogen could be used for fuel cells and transportation. And, as I say, ultimately, CO2 remediation would be important. The barriers: one has to still discover an inexpensive, stable, efficient photocatalyst. A discovery, a new invention has to be made. Nothing we have now has all of the characteristics in those three words: inexpensive, stable, efficient, that will allow us to do it. One has to learn how to practically generate hydrogen. Even more difficult, how to practically reduce CO2 at reasonable efficiencies. Then there's a huge problem with scaling this system up from a lab scale to a practical scale. And it's very difficult to get adequate resources. This is a huge problem. I think I've almost used my time, haven't I? No? So this is the basis of the system. I don't have a, I do have a voice. But basically, what you do is the sunlight hits us. This is what has to be discovered. It's a photocatalyst. The photocatalyst absorbs the light, like chlorophyll, and makes an electron-hole pair. Before they recombine, you have to pull the electron over, have a catalyst here that's going to evolve hydrogen, or in later one, reduce CO2. And then kind of shrink it into a system. This is an electrochemical cell, but shrink it into a system which is inexpensive and practical. I'll show one more, which is kind of the state of the art. This was a device made by John Turner at NRail, where he actually made a system like this using gallium arsenide and gallium indium phosphide, so expensive, not terribly stable materials, but got a 12% solar to hydrogen efficiency. If you go on his website, you can see the bubbles coming off there. So it can be made. This is not stable enough, it's not cheap enough, but the principles are there. And there have been other systems made that show hydrogen evolution, including the Kilby system some time ago. I think I'll stop here, and I think I've introduced the concept to you. And I'll look forward to hearing what the other speakers say, but I think a key problem in innovation, as we heard at lunchtime, a key problem of this is energy. Energy is the driver of all of it, and if we don't have energy, and we don't have it sustainable over the next 10 years, over the next 100 years, over the next 1,000 years, none of our other innovations are going to mean much. Thank you.